Let's take a look at this graph one more time. I can maybe even make it bigger. Let's see. This was the graph of the possible samples. This was our population mean of 24. The distance from 24 to the boundary points of the middle 80% of the samples was 2. That's why that's the 80% margin of error. And the z-score at the upper boundary of the middle 80%, which was this sample here, was a z-score of 1. So this was called the 80% confidence coefficient. The distance from the population mean to the boundary points of the middle 60% is our 60% margin of error. These two samples here, meaning these two numbers, 23 and 25, marked off the boundaries of the middle 60% because inside of here we have 1, 2, 3, 4, 5, 6 out of the 10 possible samples. And the distance from the population mean of 24 to these boundary points of 25 and 23 was our 60% margin of error, which was 1. And the z-score that went along with this upper boundary of 25 was our 60% confidence coefficient. The z-score at the upper boundary of the middle 60% is the 60% confidence coefficient, and it came out to 0.5. When we calculated it before. And I told you that if we take this z-score of 1 and we plug it into that formula I showed you earlier with the population standard deviation and the square root of the sample size, we get this margin of error of 2. If we plug in this confidence coefficient of 0.5 into that same formula, we get our margin of error of 1. So what if we had a situation in which we didn't actually have a graph of these possible samples, and we still wanted to get the margin of error? Well, I'll show you how to do that next. Before we do that, we have to think about the shape that the possible samples are following. It might look a little bit like a normal curve because it, well, you have this high point in the middle and then the shorter points at the two tails, but it isn't really a nice normal curve because it's too flattened out. It doesn't really peak like a bell curve would. But if you were drawing from a set of possible samples that actually did follow a bell curve, like this, if the boxes actually did follow a normal distribution, then it turns out that the confidence coefficient can actually be looked up in a table. For example, if the possible samples follow a normal curve like this, then the upper boundary of the middle 95%, well, I'm not going to use 95% because I want to stick with what we were doing already. We were doing 80%. It turns out that you could actually look up the z-score in a table at the upper boundary of the middle 80% of your samples. If the possible samples, meaning that all of the boxes that you're drawing from, follow a normal curve, the z-score at the upper boundary of the middle 80% will always be roughly 1.28. And I actually found that out by looking at a normal curve table. And let's compare that with what the z-score was at the upper boundary of the middle 80% in this set of samples. It came out to 1 when we calculated it. And what this says is, if these samples followed a normal curve, the z-score at the upper boundary would be 1.28. Our set of samples isn't that far from being a normal shape, which is why it makes sense that our z-score of 1 came out close to what the table gave us, which is 1.28, because the closer our set of samples is to a normal curve, the closer this z-score will be to what the table gives us, because what the table is giving us is what this z-score equals when the possible samples perfectly follow a normal curve. And I'll actually show you how I got this from the table. What I had to do was I had to go inside this table, the normal curve table, and actually find the closest decimal. And what I actually had to do first was I had to find the total percentage, not just in the middle area, but all the way to the left. And I'll explain why. The way the z-table is set up is to give you areas to the left of the z-score, meaning from the area from the z-score all the way to the left of the curve. And if the middle area is 80%, then the two tails have to be 10% and 10%. If you want to find the tails, what you do is you subtract 100% by 80%, and you get 20%. And 20% is everything outside of the center area, meaning the total of the two tails is 20%. And then if you divide 20% by 2, you split the 20% in half, and you get your two tails at 10% and 10%. And then to check your answer, you have to make sure that all of these tails add up to 100%. And these three numbers do add up to 100%. Now the total area to the left of the z-score is the center 80% plus 10% in the tail, which would be 90% of the samples. If I change that to a decimal, it becomes 0.90 if I move the decimal point. What I did was I went inside the middle of the table and I found the closest decimal to 0.9 for 90%. And it actually, the closest one was 0.8. I believe it was 0.877. No, I believe it was 0.8997. That's very close to 0.9. And what I had to do is I had to go to the row over here and the column up here. Over here I got 1.2. And for the column I got 0.8. Sorry, this should have actually been 0.08. If you piece the rows and columns together, all you do is you put the 8 after the 1.2, and when you put the 8 at the end, you get 1.28. And then that's the closest, the z-score that's the closest to this point that we were interested in up here, with 90% of the curve to the left of it. That's how I got the 1.28. So the important point is that if you know that the samples that you're drawing from, which are these boxes, follow a normal curve, then the confidence coefficient at this boundary can just be looked up in a table. Because it's, if the samples follow a normal curve, this is always the confidence coefficient at this boundary point. Now, how can we predict if the samples will follow a normal curve? Because they didn't quite follow a normal curve in this case. If you take a sample from a population that follows a normal curve, meaning if the individual people in the population follow a normal curve, then the samples also follow a normal curve. That pretty much means if these numbers here follow a normal curve, then these numbers here also follow a normal curve. If the population is normal, then the samples are normal. Also, if you take a sample of at least 30 people from a large population, then the samples are always normal. The boxes that you're drawing from would always be normal in that case. So let's take a look at an example. I recruit a sample of 40 SJSU students and record their heights. I calculate the mean height of the sample by adding up their answers and dividing by 40, and it turns out to be, let's say, 62 inches. What if I asked you to calculate the 80% margin of error and to also calculate an 80% confidence interval. If the sample size is 30 or higher, then the samples that we're drawing from at least roughly follow a normal curve, like they do here. Maybe not perfectly, but at least roughly. The guideline is if your sample size is 30 or higher, the samples that you're drawing from at least roughly follow a normal curve, which means that the confidence coefficient would just be this confidence coefficient here, which came from the normal curve table. This would be the z-score at the upper boundary of the middle 80% that we're drawing from. And if we wanted to get the 80% margin of error, we could just multiply the 80% confidence coefficient by the population standard deviation over the square root of sample size. Remember, we discovered that this formula gives you the margin of error that you're looking for. So we would plug in the 1.28 for our 80% confidence coefficient. We would multiply that by the population standard deviation over the square root of sample size. The problem is, how do we know what the population standard deviation equals? How do we know what the standard deviation of the heights of all SJSU students equals? Well, since this is just a made-up problem, we could hypothetically say that somehow we know what it equals. What if I told you the population standard deviation equals 2.8? Now we have something we can work with because we plug in the population standard deviation. We put it over the square root of the sample size. What's our sample size? We're not taking a sample of 2 people from the population. We're taking a sample of 40 people from the population. The square root of 40 is 6.32. And we can now divide this by this. .8 divided by 6.32 equals 0.44. .28 times 0.44 equals 0.56. So it looks like the margin of error, the 80% margin of error is 0.56. Let's find out what that actually means. The population mean is somewhere at the center of the possible samples. In this case, the population mean would be the mean height of all SJSU students in the university population. The distance from that population mean to the boundaries of the 80%, to the boundaries of the middle 80% of the possible samples that we're drawing from, is a distance of 0.56. So that is our 80% margin of error. Don't worry about this 90% down here, because I know it might be a little bit distracting. It's just what we were using earlier when we found the total area to the left. Now, what if we wanted an 80% confidence interval? We take our sample mean of 2.8 and we just add and subtract the margin of error, because that's what gives you a confidence interval. After adding and subtracting, we would have two numbers, and we would say the 80% confidence interval goes from this number to this number. And the confidence interval would include the population mean, as long as our sample that we selected with the mean of 2.8 with the mean of 62 is one of the middle 80%. So I think I actually did this wrong, because I said it was the sample mean plus or minus the margin of error. So the sample mean was actually 62, not 2.8, which would mean that the confidence interval goes from 61.44 to 62.56. And as long as we selected one of the middle 80% and we didn't get a sample from one of the tails, then our 80% confidence interval does cross over the population mean, meaning the mean of all San Jose State students. In order for us to calculate this confidence interval with this formula down here, you could see that we had to have the population standard deviation. This formula was for the 80% margin of error. And once we got the 80% margin of error, we added and subtracted the answer to the sample mean to get the confidence interval. But in order for us to do any of this, we had to have the population standard deviation. In a real-life situation, when you're studying a population, you don't have that number, but you have something called the sample standard deviation, which can be calculated. So what if I change this type of question, and instead of giving you a population standard deviation, I say that the sample standard deviation equals 2.8. What would we do now? Well, now what it's going to be is what we can do is we can take out the population standard deviation from the formula and substitute it with the sample standard deviation. So in this type of question, we have a new formula. It's the 80% confidence coefficient times the sample standard deviation over the square root of the sample size. Hopefully I put the square root sign around the sample size last time, because it is, regardless of whether we were using the formula we did before or this one, this is supposed to be the square root of the sample size. So now we need our 80% confidence coefficient. Last time we used 1.28 from the z-table, and it turns out that if we're using a sample standard deviation in our formula for the margin of error instead of the population standard deviation, the confidence coefficient actually won't be the same. And it's actually going to be something called a t-score, and I won't get into too much of the details of the formula for a t-score, but let's just think of that as just an estimated version of the confidence coefficient. So an estimated version of this z-score, which won't be exactly 1.28, but it'll be somewhere close to 1.28. We can get that estimated confidence coefficient by going to a t-table. So if I give you a sample standard deviation instead of a population standard deviation, the confidence coefficient comes from a t-table instead of a z-table. And the t-table is pretty easy to use. What we do is we just go down here, we go to 80%, which is the percentage I gave you for this question. That's going to be our column. We go up to the row that matches up with our sample size. I said we're recruiting a sample of 40 people. Technically, we're supposed to be going to the row that's one less than our sample size, because in a t-table, they actually set it up where each of these rows is not the sample size, but the sample size minus 1, which would mean instead of going to 40, we should be going to 39. But they don't have a 39, so let's just go to 40 instead, because that's the closest. We get 1.303, where the row and column meet up. So our confidence coefficient is actually 1.303. So since we're using the sample standard deviation instead of the population standard deviation, we had to use the t-table instead of the z-table to get the confidence coefficient. And I said it was an estimated confidence coefficient, so that's a little bit higher than what we had before. Let's take our sample standard deviation here, divide it by the square root of our sample size, which is still 40. If we complete this formula, we're going to get the 80% margin of error, because this is the margin of error formula that we're using. And once that comes out to a number, the 80% confidence, to get the 80% confidence interval, just take your answer and add and subtract it from the sample mean. So to get the confidence interval, just take 62 and then add and subtract whatever answer you got for the margin of error. And remember, the margin of error comes from this formula right here. This is how a confidence interval would be calculated in a real-life situation. You would use the sample standard deviation because that's usually all that's available to you